This video is about the block diagram level design of an amplifier for a pH probe. It corresponds to section 18.4.2 of the Applied Analog Electronics textbook. Now, I should give a disclaimer here. I have never actually purchased a pH probe and built an amplifier for it. Therefore, this design is purely a paper design and not one that has been tested in the real world. I'm not even going to take it through to the point of having a full schematic. I'm just going to do block diagram level design. And the purpose of this example is primarily to show you the steps you go through in thinking about amplifier design for a sensor. Okay, what are the two main concerns that you have when designing an amplifier like this? Well, you have to know what sort of signal are you getting? What does the input look like? And what sort of output do you need for what you're connecting up to? So let's try and make those concrete. So for the output, let's use the Teradek software on TeamCLC. And that could go 0 to 3.3 volts for the analog to digital converter on the TeamCLC. Probably want to stay a little bit away from the ends so that we don't get noise causing a little bit of clipping or loss of signal. So maybe we want to go 0.1 volts to 3.2 volts. And that gives us a little bit of headroom staying away from the ends of the analog digital converter. And Teradek can record at modest frequencies, 3 kilohertz or something like that. Okay, what does our input look like? Well, pH probes work with real chemical reactions, and the chemicals have to diffuse through a porous barrier. And so they're not very fast. They do not respond instantly to a change in pH. And as a result, we don't have very high frequency signals. But we do care about what the current pH is, even if it hasn't changed for hours. So our frequency, 0 hertz. We want to go all the way down to DC. And we might be willing to go up to 10 hertz or so. Maybe 50 hertz at the most, in order to capture basically everything that the pH probe is capable of capturing. Okay, what else can we find out about pH probes? Well, you can go on the web and read up about them, find out what the chemistry is, find out how they behave. And I found a nice source, which I cited in the book, which talked about the voltage levels that we expect to see from the pH probe. And something about the impedance of the pH probe also. It turns out the impedance is rather important here. It corresponds to about 250 mega ohms. So this is an extremely high impedance. You will not get much current from a pH probe. So you can think of it as a voltage source with an extremely large series resistance, so that you basically can't take any current from it, or you'll throw the measurements way off. Okay, so that means we definitely need an amplifier, because the TeamCLC, the analog to digital converter on that, wants something that's got less than 10 kilo ohms as the impedance driving the analog to digital converter. 250 mega ohms is way too big. So we need an amplifier. We can't just say, oh, hook it up. What about the voltages? Well, one source I found gave it as there is a voltage that it has at pH 7, a given temperature, and that they just gave an arbitrary name. And then there's a slope. There's a line it's basically a straight line with pH, negative slope, at 0.1984, and that's millivolts per Kelvin times the pH minus 7 times the temperature in Kelvin. And what this is saying is we've got something here that is a straight line whose slope depends on the temperature. And that means that in order to make a pH meter, you don't just have a pH probe. You also have a temperature sensor. And the most common temperature sensor used with these, because you need pretty accurate measurement of temperature, but not a very wide range, is an RTD, resistance temperature device, usually a platinum one, possibly something with like 100 ohm resistance at 25 degrees C. And so you measure the temperature very carefully at the same time that you measure the pH. So we're actually going to need two channels for our device, one for the pH and one for the temperature. And I'm not going to get into the design of the temperature sensor here because it's very similar to what we did with thermistors, but the RTDs have a positive thermal coefficient and more well-calibrated resistance as a function of temperature. Okay, how big is this signal that we're looking at here? Well, we can just multiply out 273.15 plus 25 times, well, if we go from a pH of, let's say we have a pH of 0 to 14, so that's plus or minus 7 for the pH, and then times 0.1984 millivolts per Kelvin. Okay, this was in Kelvin here. All right, so we're expecting to see about 414.1 millivolts for our signal. And it turns out that the way they design these pH probes, that this voltage here is usually set to be 0 volts. So we've just got plus minus 414 millivolts for their signal. Now that is actually a pretty decent sized signal, and if it wasn't for this high impedance, we could just take it directly into the TNCLC, but that high impedance means we do need an amplifier. Also, it's not in the right range, it's plus or minus, and we can't go negative with the analog to digital converter on the TNCLC. So what we're going to have is a fairly simple block diagram. We will have the probe, and coming into it is pH 0 to 14, and we're going to hook it up to VREF, a voltage that's going to be generated in our system, and we'll make it say 1.65 volts so that we have a symmetric range about our VREF signal. And then we'll have a signal coming out of here, which, depending on the pH, is going to be basically VREF plus or minus 414 millivolts. And then we're going to need an amplifier. And coming out of here, we will have 1.65 volts plus or minus. And now we wanted to say 0.1 volts away from the end, so plus or minus 1.55 volts. And that's going to go into our analog to digital converter. All right, so what gain do we need on this amplifier? Well, the amplifier will also need to know about VREF, because that's what its input and output are centered at. So this 1.65 volts that I wrote here, that could also have been written as VREF. Well, if we just look at this, the 1.55 volt range here, if we just divide that by 414 millivolts, so I'm getting 3.74. Okay, and that's really about all we will need for doing a pH probe. Is we have to hook up the probe to VREF, and then we need a small amplifier. Now, I say that's all we need to do, but it turns out things get a little bit tricky because this is such a high impedance here that this signal here is very susceptible to any sort of capacitive coupling of noise into it. So we're going to want to make this wire very short, possibly shielded to prevent it from having capacitive coupling to the outside world. A lot of times this amplifier is put right at the probe so that we don't have a long wire to pick up noise. There's a lot of difficulties involved in doing low noise designs where you've got to be dealing with very high impedance sources. But conceptually, we have a fairly simple amplifier design here. There are no filters needed. If you wanted to, you could put some filtering here to get rid of high frequency noise, but it's not likely to be enough of a problem to be needing to do anything in the analog world with it. So that's pretty much all there is to the block diagram level design of the pH meter. And again, I haven't done the temperature measurements, which also have to be done in a similar way. Important considerations to remember is that when you're doing a block diagram, not only do you need to label each of the blocks, but you need to label each of the signals with what their ranges are, what any other information you have about the signal that needs to be checked, so that I can check, hey, I've got a signal coming in here, a signal coming out here, I've got a gain here. Is everything consistent? This amplifier is reference to VREF. Are both the signals coming in and coming out reference to VREF? All these consistency checks are a really important thing to do, and the block diagram basically summarizes all the information so you can do the consistency check and not have to hold it all in your head. Okay, that's about it for this example.